Alright. Alright, we're in the end game now here. We gotta gut up for chapter 3, which is a meaty one. Yeah. And if anyone else is feeling like you got that 1,000-yard stare, last tour nom kind of sensation going, I can definitely sympathize. Anyhow, let's go with chapter 3. I have posted the review notes for chapter 3 online, so this is the video to go with it. Chapter 4 I will get done either tomorrow or the next day, but everything will be done by the end of the week. Just trying to get a bit of a head start here. Alright, so chapter 3. This is on sequences for the most part, and to a far lesser degree, series. Okay, and needless to say, you know, this is really arguably the most important chapter there is. Not necessarily in terms of like how many questions will be asked based on this, but if you do not understand the basic theory of sequences and their convergence, it will be very hard to prove a lot of the other things in chapters 4 and 5, right? Because as we saw, you know, when we talk about limits of functions, in chapters 4 and 5, it can all be tied back to limits of sequences, right? There's this sequential characterization of when limit of a function as x approaches a cluster point is equal to a certain number. Anyhow, just trying to stress that chapter 3 is very important and consequently has about as many pages dedicated to it so far in the review notes as the first 2 chapters combined. So let's start with the basic definition. So a sequence is in fact a function. F from the natural numbers to the real numbers. Okay? That's all a sequence is. A function from the naturals to the reals. And usually we write xn for f of n, or yn, or zn, as the case might be. The point being that this notation here, this f of n, is kind of cumbersome, right? So we have this kind of shorthand where it's just n appears as a subscript. All right? So that is the basic definition of a function. All right. What do I have written here? All right. So you should be prepared to provide examples of sequences satisfying certain properties. I mean, provide an example. We'll get to it, of course, but an increasing sequence, a decreasing sequence, a sequence that converges, a sequence that doesn't converge, a sequence with a convergent subsequence which nevertheless does not converge itself, etc., etc. So, among the 5-point questions, those are good ones. And in fact, in a discussion with a student today, I thought I should clarify here, or clarify rather, just inform you that I am relatively less likely to ask little 5-point questions of the sort, just give me the definition of blank. I mean, I have promised one. But the reason for that is that, of course, you'll be able to just look it up and write it down. I am much more likely to ask you to provide examples of things. So we had a couple of questions of that sort on the midterm among the 5-point questions. Expect to see more of that on the final. Okay, so expect to see very little in the way of just straight up what's the definition of such and such, or what is the statement of such and such a theorem, because that's just too straightforward for you to look up and write down. Okay, then this all-important definition, right? So the limit as n approaches infinity of xn is equal to L if for all epsilon greater than 0, there exists a capital N of epsilon, a natural number, such that the distance from xn to L is less than epsilon if n is greater or equal to this natural number, capital N of epsilon. Okay. You will absolutely be asked in one of the longer answer questions to find a limit of some sort, be it either the limit of a sequence, right, or the limit of a function as x approaches a cluster point of the domain, or possibly both, okay, because these are the sorts of questions where you actually have to work things out, and sort of every example is a bit like a snowflake. They're all a little bit different, so it's a good way to kind of test whether you've understood the material and the basic idea of the definition or not. So let me briefly go over the structure of how to answer that. So how to show that the limit as n approaches infinity of xn is equal to L. Okay, so 1. For 1 point, always let epsilon greater than 0 be given. I'm saying this for probably, 179th time in this course. Some of you will still not do this. It's still worth 1 point. Okay? So that's step 1. Let epsilon greater than 0 be given. Two, analyze this thing. Okay, so this is what you would like to be true, right? You want xn minus L, absolute value, to be less than epsilon. There's a question mark there because, of course, you have to do some work to show that this is indeed possible. Okay, so the idea here is that, let's say, the left-hand side is, or rather depends on n, of course, right? So this expression over here, after some algebraic, after substituting whatever your particular xn is equal to in there and performing a little algebra, hopefully this turns into some formula involving the n, right? And what you hope, at least, is that you hope to solve the inequality so n is on the right-hand side alone. So then the new left-hand side is your capital N of epsilon. Okay? So in a perfect world, this is some formula here involving n, and you're able to manipulate this inequality to isolate n. Over on this side, so you've got n is greater than some mess involving epsilon, and that mess involving epsilon is your capital N of epsilon. Okay? All right. That is not always exactly how it goes, of course, right? So sometimes what's over here is complicated enough that you cannot simply solve it and isolate n over on the other side, right? So sometimes you have to take a couple of stabs at what your capital N of epsilon should be, right? And N1 of epsilon just to get some minor control over what this thing is, and then a subsequent N2 of epsilon to make sure that it is in fact small and not just under control. I'm not going to go through a whole bunch of examples like that. There are tons of them, both in the text and available online, and frankly just don't have the time. But that's the idea. Part 2 is where the real meat and potatoes of the question is, okay? It is the work that you do here that will convince me that you either know what you're doing or have no idea what you're doing. Okay? And then 3, write down basically the definition of the statement, limit as n goes to infinity of xn is equal to L, with capital N of epsilon as in part 2. Okay? So just tie it all up with a bow once you have figured out what your capital N of epsilon ought to be. Okay, and in the review notes, I did carry out one example. It's not an especially difficult example because it is one of these examples where you can actually show that this inequality here, once you've plugged everything in, can be solved so that you can isolate n over here. If you want something that's a little more interesting, I mean a problem to work out, and try something like this. Show so for example, try this one. Show the limit as n approaches infinity of 1 over n squared minus n plus 3 is equal to 0. Okay? Provide an argument for that guy. That's probably not a bad one to try. Okay? All right. So that covers section 3.1. Now, section 3.2. This is on limit laws. Okay, so of course, if xn converges to L, yn converges to M, and C is some real number, then we have our basic facts. Then xn plus yn converges to L plus M. xn times yn converges to L times M. C times xn converges to C times L. And finally, xn over yn converges to L over M if M is not equal to 0. All right, so those are the basic limit laws. Probably okay, so those are the very basic limit laws, but there are a few other Facts worth noting. So you could say if, moreover, xn is less equal to yn for all n, then L has to be less than or equal to m. So the same relationship will hold between the limits of the two sequences. And you can get from there, with a little work, then to the so-called squeeze theorem, which is another limit law of sorts. Squeeze theorem. So it says that xn is less equal to yn is less equal to zn, right? So if, I should say, I guess, if xn is less equal to yn is less equal to zn, xn converges to L, and zn also converges to L, then it has to be the case that yn converges to L. So if you can sandwich a sequence, yn in this case, in between two convergent sequences, and if those two convergent sequences on the ends, the xn and the zn, both converge to the same number, L, then it must be the case that the sequence in the middle, yn, also converges to L. Okay? And this maybe is as good a time as any, then, to also mention the criterion for divergence. So we'll start first with this fact, okay, which is, this is just the negation of the statement, the limit of the sequence xn is equal to L, right? So the limit as n goes to infinity of xn is not equal to L if there exists some epsilon naught greater than 0 such that for all natural numbers n, there exists a k sub n greater or equal to n, again such that the distance from xk sub n to L is greater or equal to this epsilon naught. Okay? In other words, the limit is not equal to L if there's some fixed, strictly positive distance such that over and over again, as you go out through the sequence, you keep on finding infinitely many elements of the sequence, that'll be these xkn, such that their distance from L is strictly, or is greater than or equal to this epsilon naught, which of course is in turn greater than 0, right? So the sequence, in other words, stays away from L by this amount infinitely many times. It never gets arbitrarily close to that L, okay? So that's what it means for the limit to not be equal to L. And then, by definition, xn diverges if the limit as n approaches infinity of xn is not equal to L for any L. That is, there is no real number such that the limit, as n goes to infinity, of xn is equal to L. No real number L for which that works. Okay, so you could try proving that. Let's just say, try, if you want to test your metal, try xn is equal to n, or xn is equal to minus 1 to the n. Those are a couple of good examples, right? So both of those sequences diverge. We shall see later, of course, that this one is something called properly divergent. This one is just plain old divergent. Okay. Alrighty. In order to capitalize on the fact that, I'm not going anywhere and spending any money, I thought, I'll really try to stay away from online shopping. But it has not stopped me from making a long wish list, and it's kind of getting worse. I mean, I started out small, right? I started out wanting a pastry bag. Hear me out. You know what a pastry bag is? It's one of those, cone-shaped bags with a nozzle on the end. They usually use it to decorate a cake or whatever. But I wanted it because I was making those long tube pastas. Manicotti, you're supposed to fill them with, whatever stuffing. And the stuffing was just going everywhere. And it just looked like amateur night. I could hear the ghost of Gordon Ramsay in my ear. So I thought if I had a pastry bag, I could actually fill the manicotti and it wouldn't look so awful. Ridiculous, I know. But anyway, that's where the wish list started. Now we're up to L-shaped couch and home theater. So, the wish list is only growing. But my budget, unfortunately, is not. Anyhow, it's entertainment. Okay. So that's divergence, right. And that brings us to section 3.3. Monotone sequences. Okay. So, definition. Xn is monotone if, say, xn plus 1 is greater or equal to xn. So that's monotone increasing. Or xn plus 1 is less equal to xn, which is monotone decreasing. Okay, so either of those two situations qualifies as a monotone sequence. And then theorem. This is one of the big theorems about monotone sequences, is that a monotone sequence is convergent if and only if it is bounded. Okay? It's convergent if and only if it is bounded. But there's a little more to that theorem. Moreover, if xn is bounded increasing, then xn converges to just the supremum of the xn's, okay? This set of all the xn's is non-empty, of course, but it's also bounded above because you're assuming the sequence is bounded. Well, bounded as a set. And so then xn converges to the sup. And then semicolon. If xn is bounded decreasing, then xn converges to the infimum of the xn's. Okay, so this starting here and cycling back up to the top, that's the whole theorem. Right, so a monotone sequence is convergent if and only if it is bounded. Moreover, if it's bounded and increasing, it will converge to the sup of the elements in the sequence. And if it's bounded and decreasing, it will converge to the inf of the elements in the sequence. Okay. All right. Which brings us to subsequences. If you could look inside this box, you would be horrified. There's an absolute mountain of chalk dust over. I don't even know what all is down there, but what all is down there is now dusty. My goodness. I hope it was not important. All right. Let's see. Section 3.4. Subsequences. And, well, I'll abbreviate it this way. Subsequences in the Bolzano-Weierstrass theorem. Okay? So, first the definition. All right, so if xn is a sequence and say n sub 1 strictly less than n sub 2, strictly less than n sub 3, and so on, is an increasing sequence of natural numbers, naturals, then the sequence given by x sub n1, x sub n2, x sub n3, and so on is what is known as a subsequence. Of the original sequence xn. Okay? Right? So all you're doing is taking the original sequence xn and you're just picking off a list of elements from the original sequence, and the only rule is that you have to pick them off in order. Okay? You can skip a bunch of elements from the original sequence in between these guys, but these have to appear in strictly increasing order of index. N1 is strictly less than N2, is strictly less than N3, etc. Okay? So, that's a subsequence. Okay, so first theorem here. If xn converges to L and xn sub k is a subsequence, then x sub nk converges to L as well. Okay, so a subsequence of a convergent sequence is convergent. Moreover, it converges to exactly whatever it is that the original sequence converged to. Okay, and that gives us a useful divergence criterion. So if you would like to check if a given sequence is divergent, either of these two conditions will do. Okay, it is not necessarily the case. Not necessarily the case that a non-convergent sequence satisfies both of these, but or one of these even. But if it satisfies either of these, then it's divergent. So xn is divergent if either let's see, xn, let's see, 1, there exist subsequences, so two of them, x sub nk, x sub lk, such that x sub nk converges to L, x sub little lk converges to M, and L is not equal to M. Okay, so that's the first condition under which you can be guaranteed that xn is not a convergent sequence. That is, you can find two subsequences which converge, but converge to different numbers. All right, the canonical example is the one we went over in class a ton of times, this alternating sequence, right? So minus 1 to the n. So it goes 1, minus 1, 1, minus 1. So there's a subsequence clearly converging to 1 and a subsequence converging to minus 1, and therefore the sequence is not convergent. Okay, so that's one possibility. And continuing this divergence criterion up top here, we have part 2, which is simply that xn is unbounded. If it's unbounded, then it's not going to be convergent. All right. Then we have the two big theorems from this section. Okay? Theorem 1 is that every sequence has a monotone subsequence. And then, to cap things off, we have the big one, the Bolzano-Weierstrass theorem. Which says that every bounded sequence has a convergent subsequence. Okay? So that's one of these theorems, you know, that were we still in session, that's the kind of thing that I would, you know, kind of hope that you would be able to prove on the exam. Of course, as I've mentioned, I mean, there's really not much point in me asking you to regurgitate the proof of some famous theorem with a name, since you can easily just look it up and copy it. And so what I've decided to do is to give you that 20-point out of 200-point head start on the final exam. So, you know, you're working already at 20 out of 200. You've already got 10%, so you only got to make another 40 to get a passing grade on the final exam. Okay? All right. Which I think you should be able to do even if you have the virus. Seriously. 40%. Okay. So yeah, the university, of course, would like to have classes in session in the fall, but, you know, these giant lecture courses, like the one I'm supposed to teach, 500 people, Calc 3, those are kind of a big question mark, both for students and faculty. A lot of people packed into one place. And, you know, they're talking about, like, maybe doing things, like, would this not be an excellent opportunity to kind of hone, like, the hologram stuff? I mean, has it not been long enough that we've been watching this in movies and just kind of waiting for people to get off their butts? And, you know, we've been waiting for flying cars, waiting for holograms. I mean, so far the future is kind of a ripoff. All we got were phones. That was it. Kind of lousy. So hopefully there'll be holograms soon. All right, section 3.5, also very important, like so much of chapter 3. This is on the Couchy Criterion, right? So this is a property that you can check whether or not a sequence has. It's intrinsic to the sequence, right? So you do not need a limit. You do not need a guess at what the limit might be. This Cauchy criterion is something you, in principle, can figure out just by knowing what the sequence itself is, right? And if you can verify the Cauchy criterion, then you will know that the sequence is convergent. You will not necessarily know what it converges to, but you'll know it converges. Which reminds me of a joke. I haven't told a joke in a while. All right, I'll tell a joke. God, I'm tired. All right, so the CEO, he's got a big problem on his hands, and so he decides he's going to collect his various experts, and he's going to ask them, and then once he's got information from them, he'll have to weigh their answers and decide how to go forward. So first he calls a mathematician into his office, and he says, well, here's the problem. I need to know what 2 plus 2 is. And the mathematician says, an answer exists. So this is somewhat unsatisfying, so he sends the mathematician away and brings back the engineer. And he says to the engineer, I need to know what 2 plus 2 is. The engineer says, well, it's 1.999 repeating. And the CEO thinks about this. It's kind of a long-winded answer. He's like, yeah, still no good. Well, sends him away. Finally, he calls in the economist. He says, all right, the other two guys were kind of a wash. He says, I need to know, what's 2 plus 2? The economist kind of looks left, looks right, closes the door behind him, gets to a loud whisper, and he says, what do you want it to be? Anyhow, that's from my Uncle Jimmy. He's an actuary. Which pays well, and apparently you make money on both ends, putting pension funds together and taking them apart. Charming. Okay, definition. Xn is Cauchy if for all epsilon greater than 0, there exists some capital N of epsilon, a natural number, such that now elements of the sequence xn and xm are at distance at most epsilon from each other, as opposed to being at some small distance from a fixed limit, such that xn minus xm is less than epsilon if now necessarily both n and m are greater or equal to capital N of epsilon. Okay? All right. So that's the Couchy Criterion. Depends only on the sequence itself. And then we can summarize very briefly, despite the importance of this topic, what we really need to know about it. Okay? We need to know two things, basically. One is, how do we use it, right? And that's summarized in the next theorem, which says that a sequence is convergent if and only if it is Cauchy. And then, once that's in hand, you also would like to know when it's possible to verify that something is Cauchy. So, let's start first with the theorem. So, xn is Cauchy if and only if it is convergent. Okay, that's the big result. And then we had one type, basically, one generic type of sequence we could show as Cauchy. So we'll recall that xn is contractive if there exists a number, capital C, say, strictly in between 0 and 1, such that xn plus 2 minus xn plus 1 is less equal to c times xn plus 1 minus xn. In other words, if you want to measure the distance between consecutive elements in the sequence, the distance between consecutive elements in the sequence is shrinking. And it's shrinking at least this rate, c. Okay, so you take the distance between the two preceding guys, multiply it by this number c, which is strictly less than 1, and you'll get an upper bound for the distance between the next two guys. Okay? And it turns out that if you keep on iterating that shrinkage is happening at a kind of geometric rate. It's happening sufficiently fast that you can prove the following theorem, which is that contractive sequences are Cauchy. Cauchy. Okay? Contractive sequences are Cauchy, always. So, if I give you a practical example, say in one of these like 5-point questions, and I say, show that the following sequence is Cauchy, unless it's really obvious that you can just take the difference between two consecutive terms and it's super clear that this property holds for some c, or rather, sorry, super clear that the general definition of being Cauchy holds, then the thing you should really be thinking is, I should try to show that this sequence is contractive. Okay, so try to find a way to show that it's contractive. All right. So that is the Couchy Criterion. Then we have section 3.6. And this is a brief section on what is called proper divergence. Really just amounts to 3 definitions. Okay, so, or maybe 2. So this is section 3.6 on proper divergence. Okay, so definition. So we say that the limit as n approaches infinity of xn is equal to plus infinity if for all, say, capital M greater than 0, there exists a capital N, depending on capital M, a natural number, such that xn is greater than capital M if xn is greater than capital M if little n is greater or equal to this magic natural capital N of M. So if no matter how big a positive number you give me, I can always tell you that if you go out far enough in the sequence, then everything in the sequence after that point is going to be bigger than that giant number you gave me. Okay, and that's what it means for the sequence to converge to plus infinity. And then semicolon. We've got a similar statement for minus infinity. So the limit of xn is equal to minus infinity if for all capital M less than 0, there exists a capital N of M, a natural number, such that now xn instead is less than M for n greater or equal to capital N of M. So no matter how big a negative number you give me, I can always find a big enough natural number such that if the index of the element of my sequence is bigger than that natural number, then that element of the sequence is strictly less than the great big negative number you gave me. Okay, I can make the whole sequence less than that great big negative number by going out far enough. Okay, so that's convergence to plus or minus infinity. So technically speaking, these sequences are divergent. Okay, but they diverge in a particular way. Okay, and they therefore get a special name. And that's proper divergence. We'll just write down that definition. So definition. Xn is properly divergent if the limit as n approaches infinity of xn is equal to plus or minus infinity. That's it. So if either of those two things is true, then we call it properly divergent. So it's divergent, but in a special, particular way. Okay, and that brings us to the last section of Chapter 3. Thank goodness. So, that's the section on infinite series. All right. The section on infinite series. The first thing I want to stress, the most important thing to stress, I think, to demystify this topic, is just that an infinite series is just itself a sequence. Okay? It's just a bunch of fancy notation and fancy terminology for the question of whether or not a certain sequence converges. The only sort of wrinkle here is that you're given an initial sequence, xn say, and out of that sequence you're supposed to build a new sequence that corresponds to the series. But the way in which you do it is through these so-called partial sums, and it's very straightforward, okay? So, definition. So, xn, a sequence. Define the sequence S sub k of partial sums to be what? Okay, so here it is, right? I'm starting with the sequence xn, and I'm saying from this sequence xn, I'm going to develop, I'm going to define a new sequence. The sequence of partial sums, S sub k, which is equal to the sum from n equals 1 up to k of x sub n. Okay? Right? And that, of course, just means x1 plus x2 all the way up to x sub k. So this is the sequence of partial sums. Okay? Now, this is still the definition continued. Okay, so we've got the sequence of partial sums here. Let me not quite erase that yet. So if Sk converges to L, we say the infinite series sum from n equals 1 to infinity of xn is equal to L. If Sk diverges, the series diverges. So that all taken together is the definition of a series and the definition of what it means for a series to converge or to diverge. Okay? Now, 3 more things I want to mention, and we'll call it a day for chapter 3. None too soon. First is the Couchy Criterion. Which says that the series xn converges if and only if, for all epsilon greater than 0, there exists, and, well, let's put that on the next line, there exists a capital N of epsilon, a natural number, such that, if you look at the absolute value of not quite a partial sum, but a sort of, this actually is in fact the difference of two partial sums, okay? So instead of the partial sum starting from 1, we're going to start from some number L and then wind up at K, okay? So the series converges if and only if for all epsilon greater than 0, there's some capital N of epsilon in the naturals such that these sorts of animals, these differences of partial sums, these sums from n equals L up to K, are less than epsilon, provided that those two indices, L and K, are bigger than this magic natural number, capital N of epsilon. So all of these funny sort of partial sums are smaller than epsilon, provided that the two indices are bigger than capital N of epsilon. So that's the Cauchy criterion for series. And then a couple more things, a few more things that will allow you to make some basic estimations about whether or not a series converges. So the first of these says that if xn converges, then xn goes to 0. Okay, the elements of the sequence have to go to 0. Right, so keep this in mind. If you get a 5-point question, it has some horrible looking series, and I say, does this converge? Maybe I won't even ask why or why not. Does it converge? Yes or no? This is the first thing you should be checking, right? Because it could be a really, really horrible looking series, something you can never imagine finding a way to find partial sums for, etc. But maybe, just maybe, it's obvious that the elements in the original sequence don't go to 0. And if they don't go to 0, then the series does not converge. Okay? All right, so that's a useful one to keep in mind. We also have what are called P-series. So these are guys that look like this. The sum from n equals 1 to infinity of 1 over n to the power of p, where p is some non-negative number. So this diverges. Well, let's put it this way first. Let's say it converges if p is strictly bigger than 1, and diverges if p is less equal to 1 or greater than 0. Right? So the case where p is equal to 1, that's the sum of all the things of the form 1 over n. That's this so-called harmonic series, which we actually gave an argument for in class to demonstrate why it does not converge. And I mentioned that it's in some rough sense kind of the dividing line between convergent and non-convergent. And at least in the case of P-series, this is kind of made precise by this statement here. Okay, so what you want to do if you're forced to try to show that something actually is convergent, maybe it looks a little bit like this for some p. You know, maybe p equals 2 or p equals 1 or 3 or something like that. But if it doesn't look exactly like this, then you can employ the following, finally. And this is the last thing I'll say. Comparison. So this is the situation where we have two original sequences. Both are non-negative numbers, and xn is less equal to yn. Okay? And so xn converges. Yn, the bigger one. If yn converges, this implies that the smaller one, xn, converges. Okay? And then finally, to wrap things up, I would point out that when you have a forward implication, right, the contrapositive is always true. In other words, not this implies not this. In other words, if the xn's diverge, then theyn's also diverge. Okay, so you can use this to show convergence in a good case, or to show divergence, possibly. Okay, so the idea is that these three items here are basically the tools that we have in this course for determining whether or not a series converges. Okay, so if I ask you a question for 5 points, presumably, I'm not going to ask you a 20-point question about this. I'm really not. If I ask you a question for 5 points about the convergence or divergence of a series, then in some way, using one of these three facts, you will be able to figure it out. Okay? All right. So that concludes our review of Chapter 3. And I will try to get to Chapter 4, maybe not tomorrow, maybe the next day. Okay. Take care. Wash your hands.